Welcome to this short video presentation on our new glass-free, multiviewers, 3D display technology. To fully understand the new technology, we need to review the presently available technique used to produce the current 3D display. The lights coming from a pixel light source, such as a light-emitting diode, are diverted by a microscopic lens, placed in front of the pixel, to one of the observer's eyes. The pitch or the width of each microlens is twice the width of the pixel. Light from the adjacent pixel is diverted by the same lens to the other observer's eye. The whole process is repeated for all other pixels in the display. The lenses together form a lenticular layer in front of the pixel layer. The first pixel forms part of the first image to the first eye, while the second pixel forms part of the second image to the second eye. The diverted lights, however, do not focus and no image can be seen. For an observer to see a single image, the lights need to be focused. To achieve this, the width of the microscopic lens is made slightly narrower than the combined width of the two correspondent pixels, and the width of the lenticular layer is made slightly shorter than the width of the pixel layer. Once the lights are focused, each eye will see a single image. The two images are slightly different, and the observer's brain combined the two images together to interpret them as a single 3D image. The problem with this technique lies in the focusing method. Lights from each image can only be focused on one spot, and there can be only two focused spots for each display. As a result, only one person can see a clear 3D image. The key to our new technology is to multiply the collimated light from each pixel, so that we can have multiple focused points for multiple viewers. In our technology, 3 separate lenticular layers now control lights from each pixel. The structure of the first lenticular layer in our device is quite different from the structure of the regular lenticular layer. In the latter, the width of each microlens is roughly twice the width of each pixel. In our device, the width of the lenses in the first lenticular layer is only a fraction of the width of the pixel. The number of the microlenses covered by each pixel represents the number of the viewers. Each microlens in the first lenticular layer captures a proportion of the collimated light output from each pixel. The function of the first lenticular layer is to divide the lights from each pixel into multiple beams. Lights from the first lenticular layer are sent to the second lenticular layer. The width of the microlens in the second lenticular layer is the same as the width of the pixel. The distance between the first and the second lenticular layer is equal to the combined focal lengths of the microlenses in the two layers. In this arrangement, light beams from the first lenticular layer will be redirected by the second lenticular layers to different locations in space, each of which represents a viewing position for a single viewer. In our video presentation, there are 5 viewing positions for 5 different viewers. Light beams from the second lenticular layer then travel further towards the third lenticular layer. The width of the lens in the third layer is larger than the width of each pixel. The number of the pixels covered by the lens in the third lenticular layer represents the number of different images seen by each viewer. The third lenticular layer in the current invention is the equivalent of the single lenticular layer in the 3D displays presently available on the market. If there are only left and right images, then the width of the third lens is twice the width of the pixel. If there are more images seen by each viewer, for example, 5 different views per viewing position, then the width of the lens will be 5 times the width of the pixel. The distance between the second and the third lenticular layers is less than the combined focal lengths of the microlenses in the two layers. This arrangement is to prevent the focusing of light beams coming from a single pixel. The whole process is repeated for all other pixels in the display. Once again, the diverted lights do not focus, and no image can be seen. For an observer to see a single image, the lights from all the pixels need to be focused on the correct viewing positions. To do so, we need to slightly shorten the width of the third lenticular layer relative to the width of the pixel layer. Each viewer now can see a complete 3D picture. The 3 lenticular layers are separated from each other by transparent spaces. With the rapid advancement of 3D printing, it is possible that all three lenticular layers together with their spacers can be printed as a single unit, thus reducing the complexity of the production process. I hope you have enjoyed our video presentation, and thank you for watching.